Okay, so for part one of the problem, we were trying to find an equation, t of y, that represents the amount of time that it takes Lassie to get out to point B, which is the drowning person. So to do that, we had to find the time swimming and the time running that it takes in seconds separately. So for the time swimming, we found that it would be x squared over y squared, which is line D to line B, which would be the average there of swimming time, which is in meters divided by meters over seconds, which leaves it in just seconds. Same for the time running. It's again distance over rate, which is z minus y, which is the distance from A to D, which is how long she ran for. So we put both of those together and put it into the equation, which equals t of y. From there, we can then take the derivative, which eventually will help us find the minimum value for y. So when we were taking the derivative here, since this is to the 1/2, you bring the 1/2 down, which makes x squared plus y squared up to the power of the negative 1/2 times the inside value, which is 2y. X goes away since it's a constant, it's unchanging all over the value of s. And once again here, z goes away because once again, it's from A to C, it's unchanging. Y turns into -1 on the top, which makes it minus 1 over r. Here, the 2 comes down here, that can be canceled out, and what you're left with is an equation you can set equal to 0. From there, we tried to solve for y, which took a while, but a lot of steps. We moved the 1 over r over, made them both positive, which left us with this equation here. We then decided to square everything at once, so y became squared, s became squared, which got rid of the square root here, which was what we were looking for. R also became squared. From here, we multiplied this bottom part and brought it over up top here, which left just y squared on one side. We distributed the s to the x squared and the y squared here, then moved the r back over to the y squared, leaving us with r squared times y squared equals both values that had s in them. We then moved the s squared times y squared over, so all of the y's left in the equation were on one side. We then factored the y squared out and moved the r squared minus s squared back over underneath. We then square rooted the whole thing, took it all to the square root, which left us with y equaling s times x over the square root of r squared minus s squared. And the last thing that part 1 asked us to do was talk about the relationship between s and r and which one's bigger, different possibilities. So when you look at here, s obviously equaling swimming time and r equaling running time. If s was to be equal than r, that would give an imaginary value here when they get squared because it'll be a negative number underneath the square root, which wouldn't work. So s equaling r would obviously make the whole thing 0 underneath, which also wouldn't work. And then finally, the running time being more than the swimming time would give a positive number underneath, which would give a positive value for y, which works.
Okay, for part 2 here, the first thing that we needed to do was look at the different running times and swimming times for Elvis, and we looked at those and calculated to find the average running time and the average swimming time. And how we did that for each, what we did is we found the average of these 5 numbers and then 20 divided by that to give us meters per second, because this is seconds per 20 meters. So we got the average running time for in meters per seconds, and then we did the same thing with swimming, found the average of these 5 numbers, and then did 10 divided by that. So basically, this is R and this is S. So this is really big because we can go over here and use what Matthew gave us in part 1, and we can plug the S, and the R, we can plug those in, and we can find the relationship between Y and X. So basically, we just plug in the S right there, we plug in the R and S, we square it, then take the square root, and it gives us the relationship here. Y equals 0.13864x, and we can use that in later parts to compare the optimal point for the dog to jump into the water to where the dog Elvis actually jumps into the water.
So in the part 3 excerpt, he said that he put a tape measure here at point C, and when he was at A with Elvis, what he would do is he would throw the ball into point B, he would run down to point D with the screwdriver, and as soon as Elvis entered the water, he would throw a screwdriver in the sand to mark the point where they entered the water. He would then run down to point C and come all the way up. He would grab his tape measure, run up, and grab the distance. So in part 3, what he did is he got these 35, 36 points of data, And what we did is we so what we did is we took a best fit straight line straight through here, and then using the equation that we found in part two with Andrew, is we figured out an optimization equation. So one of the trends that we noticed is as the ball is still pretty close to the shoreline, Elvis was able to judge and optimize the best point to run down the stream or down the shoreline and then jump in the water. But as it kind of spread it away, you see up here like the optimization is just a little off. So what we could determine is that, yes, dogs understand that running a little bit and then swimming a little bit optimizes it, but judging when the ball is further away from the shoreline, it can't really judge that as well. So when the ball is closer to the shoreline, the dog optimizes the running and swimming time more efficiently.
So throughout the course of this project, we came up with about 5 limitations on what could go wrong throughout the course of this experiment. The first one that we thought of is that the dog's going to be swimming a long time during this experiment, so he's going to get fatigued. And that's something that could really skew with the data as the experiment tends to go on with more time. Elvis is going to get more tired. Another limitation that we came up with was that Timothy, the guy, was doing this job by himself. And of course, when you're doing this job by yourself, that's an increased risk of having a little bit of error involved. And we thought if he had help with other people helping dropping the screwdriver or carrying the tape measure out to point B, we would get more accurate results throughout the course of more experiment trials. The third limitation that we thought of was the variation of the wave height. So as Elvis is swimming out, the wave height could change throughout the course of the day, and this causes the times to be a little off depending on the height of the waves. And another one that we came up with, kind of more of a logical sense, is that different dog breeds can cause different swim rates. For example, the swim rate of a retriever is going to be a lot faster than the swim rate of a terrier, just because of their size. And point 5 is the graphs, kind of going off what Steve was saying. Timothy was doing this job by himself. And so this point here is where Elvis jumps into the water, and then Timothy is going to run from point D to point C. But we came up with the idea that maybe if Timothy jumped in with the tape measure to swim out to B, there could be a possibility that Elvis is already swimming back in some cases, potentially skewing with the data as well. And finally, we have a little bit of a joke. What if Elvis isn't motivated to swim throughout the course of these trials if he isn't being awarded with treats every time he does it? Because what's the point if he is not a good boy?